feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction video with Mr. Gaines here as we continue our work on linear systems. Today we are actually going to get into what is probably new content for most of you guys when we explore linear systems with three variables. So as we've done our work with linear systems, it's primarily been in reference to the Cartesian plane, where we are working with our normal XY coordinates, and we essentially are looking at lines, and we'd have two different lines that intersect occasionally to give us a single solution. So if they intersect once, we know that that is an independent system. The solution for that system would come at that intersection point, and so this would be some x coordinate, y coordinate. So some positive value on the x, some positive value on the y. So this is kind of what we've been focusing on up to this point. But it is important to note that our world is not two-dimensional. It's three-dimensional. So there's actually another version of a plane that we can examine. So here on the screen, you see a three-dimensional plane. And we're not going to go too far down the rabbit hole on this, but what we see is we see the normal x-axis and the y-axis. The x-axis is going horizontally, the y-axis is going vertically. Now we see this third axis. This third axis is a z-axis. Now it's kind of hard to represent on a flat screen, but this z-axis would essentially be coming out of your computer screen in the direction of where you're at, and so it would not be on that flat surface. Now, in this case, we can have points that exist with more than just x and y coordinates. So let's say we have on the x-axis, we have a +1, a +2. Let's say this is a +3 on the x-axis. And on the y-axis, let's say we have, let's go to -1 on the y-axis. And then on the z-axis, let's go to 2. So I could find a point that would lie off of your computer screen, if you will, that would become the intersection of these three axes. This point would have three coordinates. It would have a 3 on the x, a -1 on the y, and a 2 on the z. So here we're seeing coordinates that are no longer a coordinate pair, but technically a coordinate trio where you have an x coordinate, a y coordinate, and a z coordinate. We're going to be dealing with three variables in this topic. So let's first just take a look at finding solutions. So in problem number 1, it says to determine if the ordered triple, so the ordered triple is this expression we see here, we write it as we would an ordered pair. 1, -2, 3 is a solution to the systems shown below. So kind of like we had the ordered pair, if I just had 1, -2, my x coordinate is 1, my y coordinate is -2. With the ordered triple now, we extend that a little bit, and we go x, y, z. So my 1 would be an x, my y would be -2, and my z would be 3. So again, in problem 1, it says determine if this is going to be a solution for the system. Now, unfortunately, with our graphing calculators, our TIs, Texas Instruments calculators, we're not going to be able to graph these. Your calculator does not have the programming to graph in 3 dimensions. So we're going to have to do a lot of this work algebraically and by hand. Now, checking to see if it is a solution is not too difficult algebraically. If we know the x, the y, and the z coordinates, we can substitute into each of the equations. So I'm going to label these equations pretty frequently with letters. I'm just going to call the first one A, and I'm going to check to see if A is a solution. So let's check for A. So when I check for A, I'm putting 1 in for x. I'm going to put in -2 for y, and I'm going to put in 3 for z. So I can do this in the calculator if I need to. So I would have 1 plus negative 8. 4 times negative 2 is negative 8 minus 3. And this would give me a negative 10. And so this would be, A would be a solution, or the ordered triple would be a solution for equation A, the first equation, which is good. Now, if you remember solutions for systems, when we defined that, the solution has to work for all three, or all of the systems in the equation. So let's go ahead and let's move to check B. So this would be 2 times x, which is 1, plus 5 times negative 2, which is y, plus 8 times 3. So again, I can type that into my calculator. 2 times 1 is 2, plus 5 times negative 2 would be a negative 10, so I'll just subtract 10, plus 8 times 3, which is 24, would give me 16. And so I can see here that this, if I substitute x, y, and z into B, this is not going to work out for my second equation. So the ordered triple is not a solution. Now, it did solve the first equation, but in order to be a solution for the system, it has to be a solution for all of the equations in the system. So go ahead and pause the video for a moment and see if you can figure out if the ordered triple 1, negative 2, 3 is a solution for the system shown in B. So hopefully you've gotten a chance to work through that substitution. And we can see here that the substitution of this ordered triple into each of the three equations, which I wrote out, entitled, or labeled A, B, and C, works. And so we could say here that 1, negative 2, 3, this ordered triple is a solution for the system. So we're finding one set of numbers that, if substituted in for each of the variables for each of the equations, is going to make the equations equal. So this would be a solution. So really the option that we have for checking to see if a value is a solution is through substitution. Now, solving. Solving these, again, I discussed, graphically is going to be difficult to do. The process that we're going to solve is going to be primarily through the elimination. We are going to use some substitution when it comes in handy, but elimination is going to be our go-to method here. So if you worked with elimination in the first target, you got good at using elimination, excellent. You're ready to move forward and to carry those skills on into this target. If you are still working on elimination, we're going to see some examples here. So what we want to do, we have currently three equations with three variables. Our first objective here, and you can write this down if you need to, is to turn three equations with three variables into two equations with two variables. So let's take a look at how we're going to do that. I'm going to title this first one A, second one B, and the third one C. So I'm just going to label the equations A, B, and C. So equation C is what I'm going to look at first. Equation C here only has two variables, which is good. We know how to solve a system if we have two equations with two variables, as long as they are the same variables. So C has two variables. They are y and z. So what we want to do is we kind of want to make sure, or find a way to get A and B, combine those in a way that's going to give us just a y and just a z. So we want to eliminate x, essentially. So what I'm going to do here with A and B is I'm going to take A as it is, and I am going to subtract negative 2b. Now, I'll show you why I'm choosing negative 2b. The reason that we want to, or what our goal here again, is to eliminate the variable for x. So if I can multiply b by negative 2, that's going to give the x opposite coefficients. So I'm going to take x from, again, from equation B, I'm multiplying this one by negative 2. So x times negative 2 is negative 2x, y times negative 2 is negative 2y, z times negative 2 is negative 2z, and negative 1 times negative 2 would be positive 2. Now, I can add these two equations together. So what that would leave me with then is 2x minus 2x, which would be 0, y minus 2y, which would be negative y, negative 2z minus 2z, which would be negative 4z, and then negative 7 plus 2 would be negative 5. So what this has done, it's given me a system, or given me an equation now with two variables. So now I'm going to take this equation, negative y minus 4z equal to negative 5. And I'm going to combine that with c. So I'm going to combine that with c into a new system. Negative 2y minus z equals negative 3. So what I've done here is taken a three-variable system of equations with three equations and three variables and turned it into two equations with two variables, which we know how to solve. So we can solve this through elimination or through substitution. So I'm just going to work with this system I have written in red. I'm going to take that first equation there. Let's title this one D for if we need to reference it. I'm going to rewrite it so y is by itself. So I'm going to add y to both sides and then add 5 to both sides. So if I add y to both sides and add 5 to both sides, I'd get negative 4z plus 5 equals y, but you can reorder that. Now I'm going to take this and substitute it back into this equation that was c from the beginning. So we just moved c down here. We did not need to change that, but now I can use substitution. So I have negative 2 times negative 4z plus 5 minus z equals negative 3. Negative 2 times negative 4z would give me 8z. Negative 2 times 5 is negative 10. Still have a minus z there, equal to negative 3. Now I'm going to go ahead and combine my z's. That's going to give me 7z. I'm going to add my 10 to both sides, equals 7, and then divide by z, so z equals 1. So I've come up with part of my solution here. Z, I know, is 1. Now, I can use this z to come up with y. So I'm going to change colors here so that we can kind of follow along. I'm going to take this z, substitute it in back there. This is the equation that I solved earlier, or rewrote. So we created d, and then I rewrote d. Now I'm going to take z and put it back in there because that's going to allow me to solve for y. So negative 4 times 1 plus 5. So y is going to equal 1. Now I know z, and I know y. So I'm going to go back to the very beginning, and I'm going to take equation b. I'm going to pull out equation b, because now I can substitute in what I know for y and what I know for z, and I can solve for x. So if I take equation b and I substitute in 1 for y and 1 for z, this would be x plus 2 equals negative 1. And then I could subtract 2, so x equals negative 3. So now I have my ordered triple. Finally, I have discovered answers for x, y, and z. My ordered triple here would be negative 3, 1, and 1. So this process involves some elimination to create a system of equations like we saw in the first target. We went from 3 equations down to 2. And then we solved that 2 equations using substitution in this case. You could also use elimination. Then once we do that, we can take our values and substitute them back into any of the previous equations in order to solve for the remaining variables. I could go ahead and check these answers by substituting in negative 3 for x, 1 for y, and 1 for z, and I would see that this is going to satisfy each of the 3 equations. Let's take a look at another example. So again, I have three equations here with three variables. So I'm going to go ahead and label them again as A, B, and C. Notice this time that there is not a single equation that only has two variables. All of them have three. So I'm going to strategically choose which ones that I want to eliminate. Now C, I'm going to go ahead and rewrite this system because you'll notice that all of the variables are in different orders. So I'm just going to rewrite the system so everything's in the same order. So 2x minus 5y minus z equals negative 8. That's still equation A. Then I'm going to have negative x plus 2y plus 3z equals 13. That's equation B. And then x plus 3y minus z equals 5. That's equation C. So what I want to do here is I want to pick two equations and somehow eliminate one of the variables. I'm going to pick equation B and C because I noticed that B and C already have opposite coefficients for x. So all that I need to do here to eliminate a variable with B and C is to add them. So negative x plus 2y plus 3z equals 13, and x plus 3y minus z equals 5. If I add these two equations together, I get 5y plus 2z equals 18. So that's not something I can solve on its own, but it is a two-variable equation here. Now, it's got the variables y and z. So I used b and c. I need to use two different equations to somehow come up with just variables y and z, or think of it as eliminating x. So I did b and c already. I can't combine those again. Let me take a look at a and b because they're pretty close to having opposite coefficients for x. I'm going to take a as it is, and I'm going to double b. So if I leave a, that's 2x minus 5y minus z equals negative 8. I'm going to double b, so that's negative 2x plus 2y, sorry, plus 4y plus 6z equals 26. Now if I add those two together, that's going to give me a negative y plus 5z equal to 18. So here I have now, through elimination, I've done elimination twice, I now have two equations, each with two variables. So that allows me to create a new system. So 5y plus 2z equals 18, and negative y plus 5z equals 18. I'm going to call these equations D and E, just give them labels. Now I can either substitute or eliminate to solve with this two-variable system. So I'm going to use elimination here. I'm going to take D as it is, and I'm going to multiply E by 5. So I created these two new equations through elimination with my original system. And then I'm going to work with these two new equations as their own system. So 18 times 5 here would be 90. Now I can add these two together. And so this would give me 27z equal to 108. Now I can divide by 27, and so z is 4. So I found my answer for z. Now it becomes a substitution. Go through and substitute to solve for the remaining variables. So I'm going to take z and put it back into equation E that I labeled as E. So this would be negative y plus 5 times 4 equal to 18. 5 times 4 is 20, so I'd subtract 20 from both sides. So negative y equals negative 2, and y would then equal positive 2. Now I can take this z and this y and go back to, let's say, equation C. I'm going to go back to this equation C and substitute in for z and y. So this would give me x plus 3 times 2 minus z, which is 4, equal to 5. 3 times 2 minus 4 would be 2. And then I could subtract 2 from both sides and get x equals 3. So finally, I have come up with answers for x, for y, and for z. And so my solution, my ordered triple, would be 3, 2, 4. This would be the solution to my linear system of 3 variables. Again, I can check this by taking 3, 2, and 4, and going to my equations that are labeled as A, B, and C, substituting in for x, y, and z, and making sure they would be equal. In this case, they will. So, what we can see here is in order to solve 3 variable linear systems, we are going to need to do a process of elimination to create a 2 variable system. So that's what we did here first, combining B and C and A and B. Then we can use our previously learned methods to solve that 2 variable system for a variable, using substitution to figure out the remaining variables. This is a pretty good place to stop for right now. As we start and continue through this, we'll see some more examples, and we'll take a look at some applications of 3 variables. As always, thank you guys for tuning in, and I'll see you soon.